Okay. Okay. So can you see my screen? Can you hear me?
Everything's good.
Okay. Thank you. Okay. Good morning, good afternoon, and good evening, everyone. Greetings from Singapore. Okay. So I'm Shen Yong, and I was David's PhD student from 2004 to 2009. So it's good to see familiar faces. Hi, Peter. Stain, Joe, Juliana, and Hubert. My deepest sympathy to David's family. I'd like to take this opportunity to thank David and Yuna for looking after my family and I while I was doing my studies at U of T. So now I'm at the School of Physical and Mathematical Sciences, Nanyang Technological University in Singapore. So we're exactly 12 hours ahead of Toronto's time. I'm also spending more time actually in education. Actually, for the last 10 years, I've been spending the large part of my time in education. But I think I remember enough of my PhD thesis to do this presentation today. I'm now also with the Institute of Pedagogical Innovation, Research and Excellence. So if you are interested in education, maybe we can connect. Yeah. So while I was preparing the talk for today, I was just looking through some of the past papers that David has published, and some, especially those related to approximations and oscillators, and this paper popped up, so I mean, if you're familiar with David's work, this is his famous 1968 RPA paper, and part of this. It's actually in his book, Nuclear Collective Motion. And so I'm not sure whether Yuna is here. I think she probably helped type part of this in the book. And I was looking at the sites for this paper, and it's very interesting that more than 50 years after, the number of sites from his 1968 paper is still very significant. I mean, just look at 2022. We have a number of papers, okay, in quite a different area. Okay, and now the paper was on nuclear physics, but here we have other applications in quantum computing and chemistry and so on. So I think David's work has far-reaching impact in many areas in physics research and also even beyond physics. Okay, so the main topic for today's talk is actually on this paper. So it's very interesting to see Chen Hong here. I've never seen Chen Hong before, so this is the paper that I was working on as part of my PhD. Towards the end of the paper, there was this little few paragraphs that spoke about this oscillator approximation that formed the main bulk of my thesis, actually. So this was in 1990. Okay, so it's essentially a harmonic oscillator approximation, and you probably recognize that there is some Taylor expansion and so on. So I'll say a little about this approximation, and I will also say how it is related to the thesis that I did. Okay, so using, okay, so there's a reason why it is shifted its grade. Okay, so I'll explain a little later. So here we have a harmonic approximation, and I'm going to use SU2 operators as example. Okay, so considering representations of SU2 operators in the JZ diagonal basis, we can okay, it can be written this way. Okay, and if we have a Hamiltonian with SU2 operators, okay, the eigen vectors, okay, can be expressed as a superposition of the basis states. Usually when we solve for the eigenstates of a Hamiltonian, you'll be interested to work out the coefficients of the basis states. Okay, now we can make an approximation, assuming that x is a continuous variable, especially if j is large. Now we can see that this distribution can be approximated as a function. Okay, so what we had just now, okay, can be expressed as an approximation, and it becomes a function jz times this function. Okay, for j plus minus raising and lowering operators, the coefficient can be treated as a shift. Okay, and then we can do a Taylor expansion. No, just for the first few terms. And this is what you get. Okay, but here there is a little limitation, because here we require x to be quite small, close to 0, okay, for the approximation to be good. Okay, and now if you look at problems, typically, the value will be centered around some other value that is away from 0 here. Okay, so I had a chat with David, on how we can improve this. So, well, he mentioned in passing, why not expand it about the minima of the potential? But of course, here we do not know beforehand what is the minima. Okay, so here you're seeing the exact results that is obtained from diagonalization. So how do we construct an approximation such that we can do the expansion about this unknown minima? Okay, so it got me thinking. Okay, David's words on expanding this about the minima of the potential got me thinking. Well, I think after a few days or weeks, okay, it dawned upon me that there is actually a way out of this, finding this unknown minima. Okay, so if instead of expanding about x equals 0, you expand it about an unknown x naught, this is how the expansion will look instead. Okay, and if you rearrange terms in the Hamiltonian, generally you can write it in the form of a shifted harmonic oscillator. And it will look something like this. Okay, and now it's going to be centered about x naught, so we're using x prime instead of x, so a shift is being done. Okay, but if we set the minima of the potential to be at x equals x naught, now the origin of x prime will be shifted to x naught. So in that case, there is no shift in the x prime coordinate. So d here, okay, that is related to the shift term can be set to 0. Okay, and if you use this in reverse, we can set d to 0. Okay, insisting that there is no shift about this new coordinate system, and then that will enable us to solve for x naught. Okay, and from there you can actually derive the coefficients of this A, B, C, D of this quartic oscillator approximation. Okay, so using this so-called canonical Josephson Hamiltonian, this is something that I learned in a conference that I attended when I was a graduate student. I learned it from a fellow Mexican PhD student in this Canada, American, Mexico conference. So very interestingly, the person who came out with this Hamiltonian became my postdoc supervisor after I graduated. So this is like a typical Hamiltonian written out of SU2 operators. Okay, so if you apply what that was suggested, this is what you get. Okay, the shifted harmonic approximation of the CJH can be written in this form. And this term here, corresponding to the shift term, okay, can be set to 0, because here we insist that the origin is going to be at x naught. So if we solve for x naught, there are a lot of other things that we can get. Okay, so if you're familiar with the harmonic oscillator, knowing the coefficient will enable us to know the excitation energies, the ground state energies, the spread, and allow us to write the wave functions. So H here is the Harmonic polynomial, and here we insert a normalization term, okay, such that yeah, it's the sum of all the terms for discrete m will be equals to 1. And you can put it back, into the original expansion. Okay, and so this will give you the estimation of the the coefficients. So essentially, this is the shifted harmonic approximation. Okay, the results are quite good. If we applied to the canonical Josephson Hamiltonian, for one symmetry limit, you see that the fit is quite good. Okay, the crosses represents the exact results, and the blue axis represent the approximation. Okay, and it worked well for a whole range of values for one of the parameters, and it's across different symmetry limits. Okay, and we can extract easily the excitation energies, the ground state energy, and we can even get some insights, in different limits. For example, if epsilon j is small and it approaches 0, okay, the first term would vanish. Okay, and the term here would also vanish, and this is what you'll be left with. And this is in the Fock regime of the Hamiltonian. And this resembles a particle in box self-energy. Okay, so here I'll just call it the standing wave approximation. And you see that it gels very well with the exact values in both limits. Okay, both in the Rabi limit and in the Fock limit. Okay, and for a fixed value range of mu, okay, we can check how the approximation works for a whole range of k. Okay, and the approximation works very well, but at sort of like a transition point, you see it starts breaking down. Okay, but if you use the standing wave approximation, okay, for large value of k, it works well again. So here, if you drop the first term in the SHA, you get something interesting that works again. So here are some graphs, again, showing exact values and predictions using the SHA. Okay, and here it's for the minimum of the potential. So it's compared against the exact minima. Sorry, here is the mean of the exact values for the first excited state. So you see that the values matches all very nicely. Okay, so this is the ground state energy, this is the excitation energy. Okay, so I was very excited at the end of this set, and everything worked out very nicely. I got something to write and to be able to graduate on time. Okay, I tried a few other things. So one of which I think Peter will be familiar with. This quite a large part of this is taken from Peter's paper with David with regards to phase transition of the spherical vibrator to the gamma soft rotor. Okay, so this is the Hamiltonian in question. Okay, there's a bit of details, but the focus would be on this term alpha. So if alpha is less than 0.5, it is in one phase, the spherical vibrator. And if alpha is greater than 0.5, it will be in the gamma soft rotor regime. Okay, so this Hamiltonian can be expressed in terms of SU11 operators. And here we'll just be working with models with the same seniority. Okay, there's no crossing of seniorities. Okay, so just to see the effect of different alpha on the potential. Okay, so 0.5 is the dotted line, dashed line. Okay, and if it's less than 0.5, it would be the minimum would be at 0. Okay, but if it exceeds 0.5, the minimum will shift away from 0. So this is like a little like the Mexican had spontaneous symmetry breaking type of potential. Okay, so it takes this form, and now this is the matrix representation for SU11 operators. Here we have a parameter lambda written in terms of the seniority. So if you apply the SHA for this quartic oscillator using the same principles, but make some adjustments when you go from SU2 to SU11. So these would be the terms that you get for A, B, D, and E. And you can do the usual to solve for, so set B equals to 0 and solve for N naught. Okay, I mean, yeah, I typically use a computer to solve it. Okay, I don't think you can solve it by hand, but there are certain limits that you could apply this, and it works quite well. Okay, so for alpha greater than 0.5, we need N naught to be positive, and in the limit whereby your N naught is much greater than lambda, you could make some very simple approximation, and you get nice and simple results. Okay, and for very small alpha, okay, and a relatively large M, okay, the second term would disappear, and you're just left with front. And if you again set it to 0, okay, you can solve for N naught, and from there, you can actually get your range of expressions, and from there, you can get the approximation for the excitation energy, and if you derive this using the RPA, you also get the same expression. Okay, so I tried doing this experimentation across a range of alpha for 2 distinct values of amps and 2 seniorities. The cross and the blue dots, these are exact values that you get from diagonalization. The line is what you get from SHA. And you see that the fit is actually very good. Okay, that's for N naught, guessing the minima, approximating the minima of the potential. And then here we have E naught, which is the ground state energies. Okay, the excitations energy. So it's sort of, well, it's a little off, at the turning point here, where you have a phase transition. Okay, but on either ends, it seems to have worked pretty well. Okay, and for sigma, which is the spread of the wave function. Okay, so this is second thing that I tried on. So the last thing that I worked on was the VCS Pairing Hamiltonian. Okay, so this is the form that you usually see if you read a condensed matter paper on this topic. But in nuclear physics, typically it's written in SU2 quasi-spin operators. So you can set up a multi-level problem. Okay, so here I've just like a 4-level problem, and 4 single particle energies, and the J will actually indicate the maximum occupancy of each level. Okay, so if the level is totally empty, M will be equals to minus J. Okay, and if it's totally full, M will be equals to J, and everything else is in between. Okay, so if you have R level system, okay, sum to R, M pairs, we have these operators that scatter from level Q to P, and this number here is actually the corresponding interaction strength. So if we have a multi-level problem, we can actually construct a basis, okay, that has components, one for each level. And this it's a multiple copy of SU2, and this is the algebra. So if you apply the SHA to the VCS Hamiltonian, after working through the algebra, this is what you get. So the first term here is actually an inverse mass tensor, and B is a spring constant tensor. D is a set of sheaves, and E is actually the ground state energy. So if you diagonalize the first term to decouple the system, you find that you always get an eigenvalue of 0 and corresponding to a vector in the direction that's normal to the hyperplane. Okay, and in this hyperplane, actually, we can keep the number constant. Okay, so we can actually, this is a little strange, if you're a condensed matter person, because the pair number is not really conserved. You just look at the expectation value of the pair number. But here, we actually have a mechanism whereby we can actually fix the pair number, and this would be of probably greater relevance in nuclear physics. Okay, so this is how it looks for a two-level VCS model. So here we have M1, M2, two levels. Again, the dots are the exact values, and the line is the SHA approximation. So here, A and B are two different interaction strengths. Okay, so B is a weak interaction, and A is a rather strong interaction. So you see that the SHA works quite well, okay, in these two domains. And C correspond to a different particle number. Okay. So if you toy around with this, and because the original VCS theory has its own set of prediction, we can actually do a comparison. Okay, so if we just work with a toy model of 4-level, 28 pairs, okay, and these are the maximum occupancies for the 4 levels and the corresponding single particle energy levels, and if we just write some expression for the interaction strength, now we can actually turn the crank, put this in a computer, and you just get an answer if you just diagonalize. Okay, the number of basis states is about 3,200. Okay, at that time it took about 10 minutes to diagonalize this matrix. I've got 4 gig RAM on my laptop then, but you can do this actually on a laptop on MATLAB, using MATLAB. Yeah. Okay, so I did the computation across a whole range of interaction strength. Again, the crosses are the SHA predictions, and the diamonds are the exact values. So the match is good. So this is for determining the minima of the potential, and the average value for the wave function. Okay, here we also do a comparison with the original VCS theory, okay, with Barton Cooper Schiffer theory. And we see that the prediction from SHA follows very closely to the exact results over a whole range of interaction strength. Okay, similarly, for the ground state energy. Okay, so here again comparing exact results with SHA and the VCS prediction. Okay, so I won't bore you with the details, but now we can see a lot of similarity but unique features of the SHA as compared to the original VCS Hamiltonian. Okay, so I think now I'll wrap up. Now, I've showed you, the shifted harmonic approximation, applied it to the canonical Josephson Hamiltonian, and also to the spherical vibrator to gamma solved rotor transition. And lastly, we look at the multi-level BCS Hamiltonian. So the SHA can also be obtained, can also be used to make estimations of Clebsch-Gordon coefficients. I think David and Hubert published a paper in 2010, so you can actually refer to this paper for more details. Okay, so if you're interested, either in physics education or the SHA, you can drop me an email. So that's all I have, for today. Thank you.
Thanks. Are there any questions or comments?
Yes.
Hi, Yubei.
How are
Yubei
you?
was my external examiner.
Yes. So, yeah, this is the last paper I worked on with David.
Oh,
Yeah. Okay, so this is the last paper I worked on with David, and
you're right.
I was external examiner.
Why does it work so well?
Yeah, that's something that we had a hard time trying to explain, and it actually held us back publishing the paper, actually. So why did it work so well? It's something quite strange that we can't really explain, because we started off with a large J approximation, assuming that the thing is continuous. So if I just scroll back, so if we go to this, okay, so here the trick that was done. Okay, so this is on two different phases, in the CJH. Okay, so we started off with this continuous approximation, large J, and it seems that the part here about determining the minima doesn't require the distribution to be continuous. So in fact, when the first term was dropped, and this is what is left, it continues to work. Without this is not really an oscillator now. I mean, just dropping the first term, and we got like a standing wave approximation. So actually, one of the things I wanted to do, but I didn't have time to do it, was actually to look at difference equations. Okay, and also wanted to explore to other differential equations and see, if this technique is applicable. But unfortunately, I didn't have time, and I wanted to write this. David has been asking me to continue writing this paper. It was in 2013, 2015, but I didn't have time, and I think it's probably, I don't have an easy answer to your best question, why it works so well, actually. So I'm not sure. We may need the help of a mathematician to examine this more closely. Maybe I should have a chat with Joe as well. Yeah. Hubert, do you have any insights?
Well, I was, hold on, this is, okay, sorry. This is, like this?
Okay.
There's still some echo here, so. Okay, so like if you're going to go the route of the difference equation, then some difference equations they have kind of WKB style relations to them, and which is sort of like some kind of and that could explain it, but it's still quite. I mean, like you basically got you know, like last digit accuracy on something that's just very, very simple. So like, I don't know, but this is okay. Anyways, it's nice to see you again. So
Yeah.
Yeah, I have,
Okay.
so in your the quartic oscillator, you have a parameter beta, and you're calling it the Hill-Wheeler. Is that this? Would that correspond to the quadrupole moment?
Yeah.
Collective model.
Yeah. Yes. I think more details can be found. Okay, let me just pull out the paper. It's well, Peter was one of the co-authors of this paper. Okay, let me just drag this over. Okay, give me a second. Okay, I'm having multiple screens and okay. Yeah. Yeah, so it's taken, well, I got the Hamiltonian from this paper. Peter and David wrote this paper in 2005. And well, the details, yeah, the details are in this paper.
Are there any more questions, comments?
This is to get my camera to work here. Oh, Zoom. I'm sorry, you have to do with just my voice here. So first question is, when are we going to write the paper? And when are we going to write the paper? And the second, well, maybe Hubert just left the room, but one of the things that, reasons why I understood that the approximation worked so well is that this is a collective effect, that you have very like large amplitudes and very smooth amplitudes. So one of the things that you see is that for large representations, it will work better because your space, you give it more room to give it a collective oscillation. And an SU11 is ideally made for that because the representation space, for instance, is huge.
Yes. This is Stan, right? Is this Stan talking?
Yeah, it's me, Stan.
Okay, good. Yes.
How are you doing?
Good. You look younger.
So maybe we can take that offline, or you can use the chat.
Yes, we will.
Let's.
Okay, I'll stop sharing.